Hello everyone. Today we are going to learn how to validate logic arguments using what's known as Euler diagrams. Now previously we had learned how to validate symbolic arguments using truth tables and truth values. Symbolic arguments contain statements with words as and, or, not, if, then, if, and only if, which were the conjunctions, the disjunctions, the negation, conditionals, and biconditionals. And in order to validate such arguments, we had to build truth tables and then use the truth values to come to a decision whether the arguments were valid or a fallacy. Euler diagrams, on the other hand, work with a special group of arguments called the syllogistic arguments. And syllogistic arguments have statements with words or phrases as all are, not all are, some are, none are, and so on. Right? And in order to validate syllogistic arguments, we use the Euler diagrams. Now, Euler diagrams gets its name from the Swiss mathematician Leonhard Euler, who made many contributions in the field of not only mathematics, but also physics, astronomy, and so on. And one of his many contributions was the Euler diagrams, which can be used to validate syllogistic arguments. So what are Euler diagrams? They're very similar to Venn diagrams that we had studied about when we were learning set theory, right? So the diagrams, the Euler diagrams, will vary based on the phrasing in the statements of syllogistic arguments. So let's look at the first phrase here, which says all A's are B's. How would the diagram for this look like? First, let's try to understand what this phrase means. It means all elements contained in A are also a part of the set B. All right. So the way we would go about drawing this is we would have a circle. We would have a circle representing the set A, and every element in set A is also a part of set B. All A's are B's. So we will show that by drawing an outer circle completely encapsulating set A, and we'll name that outer circle B. So this represents the fact that every element in A is also a part of the set B. All right? Now let's try to draw the diagram for the phrase no A's are B's. All right? So this means that none of the elements of A's are a part of the set B. Correct? So the way we would go about drawing this is we first draw our circle or set A with its elements. And because none of these elements are common to B, all right, not even a single element in A is a part of B, we will draw the circle for set B. However, we will keep it separate. All right, so they do not intersect. There's nothing common in it. So they will be spaced out as two circles, all right, separated from each other. These are disjoint sets. How about the next phrase, which says some A's are B's? What this means is there are some elements within A which could be a part of B, but not all of them. All right, so the way we will go about representing this with an Euler diagram is we'll draw our circle for A. All right, we'll draw our circle for A with its elements. Let's put some more elements here. And some A's are B's means there could be some elements within A which also are part of B. So there would be an intersection involved. So the circle the circle B would intersect, would be partly linked with the set A. All right, so this is our B. So we have an element here which is common to both set A and set B. It falls in the intersection between the two sets. However, there are elements in A which are outside the intersection. All right, so that means some A's are B's, but not all A's are a part of B. So the next phrase is some A's are not B's. How would the diagram for this look like? It's going to be similar to the one which we drew before. Some A's are B's. However, here our focus is the elements which are in A but not in B. So let me draw the circle for A first. So we have our circle for A, and we will also have a circle for B which will intersect with A. All right, so this is our circle for B. But since some A's are not B's, is the phrasing, we will have to show the elements outside the intersection region, all right, outside the intersecting region, so to speak. So the elements that we are referring to when we say some A's are not B's are the ones that are outside the intersection between A and B. They only belong to set A but not to set B. All right? We'll now work through some examples to determine whether the given arguments are valid or not using Euler diagrams, right? So the first thing that we are going to do is read through the argument, and then we'll create an Euler diagram based on the two premises, and then we'll draw one which also includes the conclusion, all right? And then we will compare and see whether they match or not to decide whether they are it's a valid argument or an invalid argument, right? So let's read through it first. It says all planets are satellites. That's the first premise. And then we have the next premise saying Picard is a satellite. And the conclusion is therefore Picard is a planet. All right. So first I'm going to draw the Euler diagram just for the premises, right? So the first premise says all planets are satellites. And that picture is going to be similar to the one that we drew up here. All A's are B's, correct? So I'm going to draw a circle for planets, and that circle is going to be contained entirely within the circle of satellites. So satellites is the bigger set, and it contains the set of planets. Every planet is also a satellite according to the first premise. And then the second premise says Picard is a satellite. All right. Now, since it says Picard, whatever that is just a satellite, we have to, Picard is just an element, right? We have to show Picard somewhere within the circle of satellites. All right. This is Picard. But it's not within the circle of planet, because nowhere in the premises it's mentioned that Picard is also a planet, correct? So you have to draw that within the circle of satellite, but not within the circle of planets. All right, so that completes the Euler diagram for the first two premises. Now I'm going to draw this picture again, but I will be including the conclusion within this picture. All right, so this is how it's going to be. It says, therefore, Picard is a planet, correct? So if that were true, if that were valid, then the picture would be like this. The picture would look like this. We have our circle of planet. Outside, we have a a circle around for satellites. But when we include the conclusion, the argument, Picard is a planet, then Picard should really belong here, right? Picard should really belong within the circle of planets. However, the premises, all right, this picture, which is based on the premises, shows that Picard is within the circle of satellites, but not within the circle of planets, correct? So these two diagrams do not match, all right? No match. Therefore, the conclusion should be that the argument is a fallacy. It's an invalid argument, also a fallacy, all right? Let's take on another example. This one says no PCs are Macs, and then the second premise says all Dells are PCs. The conclusion is, therefore, no Dells are Macs. So we have to decide whether this is a valid argument or not. Again, we'll start by drawing the Euler diagram for the two premises rather, all right? So we'll go one at a time. No PCs are Macs. So how would this diagram look like? This would mean that we have two sets here. We have one for PCs, this PC, and then another one for Macs. But since no PCs are Macs, it's going to be a diagram that's going to look like the diagram we drew above. No A's are B's, correct? So let's go down here. Let's have another circle for Macs, but they have nothing in common. No PCs are a part of Mac. There's no intersection, so they have to be disjointed. All right, they have to be separate circles without any links between the two. And then the next one says all Dells are PCs. All Dells are PCs means there's another set of elements named Dells, that set, and that will be contained within the circle of PCs because every Dell out there is also a PC. So let's draw a circle that will represent Dell, all right? Dell computers, correct? So this is the Euler diagram just for the two premises, right? Now let's draw the Euler diagram that will include the conclusion in it as well. All right. So it says no Dells are Macs. That's the conclusion. Again, let's draw the diagram. We will have one for PC. All right. Again, this is our PC. And then we have the circle or the set for Dells. And then we will have the Mac, which is a circle, disjointed circle. Correct? And no Dells are Macs. So this picture here is showing that the Dell computers, have nothing to do with Macs. It's in no way a part of Mac. So this picture here, all right, this picture matches exactly with what we have above based on the two premises. Therefore, the conclusion is that this is a valid argument. It's a valid argument. The Euler diagrams match, correct? There is a match. All right. Let's look at another argument now. This one for the first premise reads as some mushrooms are poisonous. And then the second premise says a morel is a mushroom. And then the conclusion is therefore a morel is poisonous. All right. So again, we will first draw the picture, the diagram for the first two premises. Some mushrooms are poisonous. So here the bigger set is everything that is poisonous, that would be regarded as poisonous. So we are going to have a circle representing elements that are poisonous, right? And then some mushrooms are poisonous. So there's going to be a circle for mushrooms, but that circle is going to partially intersect poisonous elements because not all mushrooms are poisonous, only some mushrooms are. So here I will draw my circle for mushrooms partially intersecting with poisonous things. All right, so here I have my mushrooms, the circle for mushrooms. And then the second premise says a morel is a mushroom. Now, nowhere in the two premises it states that a morel is poisonous. It could be, but the premises don't state that. Therefore, we have to place the morel outside, all right, outside the region of intersection, but within the circle of mushrooms. All right. So this is the picture that we get, the Euler diagram that we get from the two premises. Now we are going to draw one which will also contain the conclusion. All right. The statement of the conclusion. So again, we'll have our circle for mushrooms, and which will intersect with the circle of poisonous things, okay, poisonous items. And then the conclusion says a morel is, therefore a morel is poisonous. All right. So based on the conclusion that morel should be placed within the intersecting region, correct? Morel should be within the intersecting region, a part of mushrooms, but it should be within the part that also intersects with poison. All right, poisonous items. A morel is poisonous. So now let's compare these two pictures. All right, so this picture here that we drew, the second picture, is not the same as the one that we obtained from the premise, correct? So the pictures don't match, no match. Therefore, the conclusion should be it's an invalid argument. Doesn't match, all right? It's a fallacy, in other words.